In this video, we're going to be talking about Gabriel's horn and the painter's paradox. First, let's consider the graph of the function f of x equals 1 over x for all values of x that are greater than or equal to 1. Let's go ahead and graph this. So if we're looking at the graph of y equals 1 over x for all x values greater than or equal to 1, if I plug in 1 into that function, my output is going to be 1. And it's a decreasing function in the first quadrant, and I know that there's a horizontal asymptote at y equals 0, or the x-axis, so my graph is never actually going to reach or touch the x-axis, but it'll get infinitely close. Now, suppose that you rotate the graph that is bounded by the function and the x-axis on the given domain about the x-axis. So we're going to rotate around the x-axis. This will create a three-dimensional shape that resembles a horn or trumpet or vuvuzela. All of these are musical instruments. So let's take a look at what the graph of that three-dimensional shape would look like. Here's a much nicer image of what that three-dimensional shape is going to look like. Part A of this example wants us to find the volume of the horn. And it might have been a while since we've utilized this, but when we're finding volumes of solids of rotation, in this case, we're going to end up using the disk method. So what I'm going to do is I'm going to draw a disk here, and it's going to have some thickness to it. And the thickness we can call dx or delta x. And the radius of this disk is going to be the y value of the function. But because our cross sections are stacked side by side, we're going to be integrating with respect to x, so it would be helpful to think about our radius as, instead of y, thinking about it as 1 over x. So let's work on part A now. We have that the volume is equal to, because we're using the disk method, we're going to have pi times the radius squared. I'm going to factor out pi, and we're looking at x values that are greater than or equal to 1. So I'm going to have my lower limit of integration be 1 and my upper limit of integration be infinity. So it turns out that this is an improper integral. And then we have the radius squared dx. So let's go ahead and rewrite this as pi times the limit as b approaches infinity of the integral from 1 to b of, and if we square that, that's going to give us 1 over x squared dx. And I'm going to rewrite this as x to the negative 2 power so that it's easier for us to use the power rule. So we have the volume equals pi times the limit as b approaches infinity of our antiderivative will increase the power by 1 and divide by that new power, which will give us negative 1 over x. And we're evaluating this between x equals 1 and x equals b. So this is equal to pi times the limit as b approaches infinity of negative 1 over b minus or plus, because it's going to be subtracting a negative, and then we have 1 over 1. Now, what's going to happen as b approaches infinity? We have this fraction here, and as b gets really large, because it's in the denominator, this fraction will go off to 0. And so we'll have pi times 0 plus 1, which is just equal to pi. So our volume for this horn is pi, even though this is an infinitely long horn. Its volume is pi. Now part B says, find the surface area of the horn. So for B, we're going to set up our integral. We have s equals, our limit of integration is going to be 1 to infinity of 2 pi, and we're rotating about the x-axis, so we're going to have y here, and we have the square root of 1 plus. We know from earlier that our function is y equals 1 over x, which is the same thing as x to the negative 1 power. Let's go ahead and take the derivative now. So I'm going to bring the power down, and then decrease the power by 1. So we have negative 1 over x squared. And if we square that, that's going to give us 1 over x to the 4th power. So I have 1 over x to the 4th power dx. Now, because we're integrating with respect to x, I don't want this y here, so I'm going to rewrite this as 2 pi times 1 over x. Now, our goal is to integrate this thing, but it turns out it'd be quite challenging to proceed with integrating that. So what we're going to do instead is utilize something that we learned in the section on improper integrals. And I'm going to compare this using the direct comparison test for integrals using a function that is much easier to deal with and that we know something about. First off, I'm going to factor out 2 pi since that's a constant, so we don't need that inside of our integral. Okay, so what are we going to compare this to? And do you think that this improper integral is going to converge or diverge? Who knows, but let's start off by thinking about the square root portion of our integrand. So I have 1 plus 1 over x to the 4th power, and something that we want to recognize is the x values that we're looking at in this particular case are or belong to the interval 1 to infinity. In other words, all the x values that we're looking at are positive numbers. Now, if I plug in a positive number into x here, what's going to happen is we're going to get 1 over x to the 4th power is some positive number. And if I add 1 plus some positive number, that is going to be some number greater than or equal to 1. And if I take a square root of a number that's greater than or equal to 1, then whatever that square root is going to be greater than or equal to 1. Now, why do I care about that? Well, this implies that, and what I'm going to do essentially is I'm going to take this inequality and I'm going to multiply both sides of the inequality by 1 over x. And it's important to note that 1 over x is a positive number, so it's not going to flip our inequality sign, and it's going to stay the same. So 1 over x times the square root of 1 plus 1 over x to the 4th power is going to be greater than or equal to 1 over x times 1, which is just 1 over x. Why do we care about this inequality? Well, based off the direct comparison test for integrals, this is going to imply that the integral from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th power dx is going to be greater than or equal to the integral from 1 to infinity of 1 over x dx. And we know something about this second integral. We know that by the p-test, you got a name drop. So by the p-test, this diverges since p is equal to 1. So this is the smaller of the two things that we are looking at. And if the smaller thing diverges, then the thing that's greater than or equal to it must also diverge by the direct comparison test for integrals. So again, to reiterate, by the direct comparison test for integrals, the integral from 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the 4th power dx must also diverge. So what does that mean? Well, the implication of that is therefore the surface area of this infinite horn is infinite. So coming back up here, the surface area is infinite. So again, this example is called Gabriel's horn and the painter's paradox. Gabriel is said to refer to the archangel Gabriel, who blows the horn to announce Judgment Day in the Christian religion. This is called the painter's paradox because the volume of this infinite shape is finite. It happens to be pi, but the surface area of it is infinite. That means that if you took this infinitely long horn, you could fill it with a finite amount of paint if you poured it down the spout, but you would need an infinite amount of paint to paint the outside of the horn. Isn't that fascinating? That concludes this really cool and wonderful example.